Okay, are we good to go here?
Yes, we are.
Okay, great. So let's see. I gotta hit this button to get it going. Yeah, so I just want to thank Mike again for inviting me to speak tonight. As I said a few minutes ago, it's nice to be able to at least meet with the club virtually if I can't be there in person. And I want to thank the Gloucester Area Astronomy Club. It's always fun to reconnect with GAAC, and hopefully one of these days when the pandemic ends, I can travel up to Boston and see all of you in person. And I just want to thank all of you for tuning in tonight, wherever you are. So my objective for my talk tonight's presentation is to demystify black holes. These strange objects have captured the public's imagination since the 1970s, when I was in junior high school and then senior high school. And they've become a staple of science fiction stories and movies. And as just one example, and I rented this movie actually just a few months ago, is the movie made by Disney. And by the way, I used to work for Disney when I was at Discover magazine, when it was owned by Disney. They made a film in 1979 starring Maximilian Schell called The Black Hole. So I didn't watch it back then, but when I rented it and watched it a few months ago, I actually wasn't that crazy about it. It was kind of creepy. It was kind of a silly storyline. Didn't really have much to do with black holes. I mean, there was a black hole in the movie, but the movie really wasn't about black holes. But I would give much higher marks to 2014 movie Interstellar, which I thought was a very well conceived and well acted drama. The chief scientific consultant was Kip Thorne, who, as I'll talk about a little later, was the co-recipient of the 2017 Nobel Prize for Physics. Now, since we're in a joke mood here right now, there's a joke that there's only two places in the universe where the laws of physics do not apply, and that's inside black holes and in Hollywood. But unlike most Hollywood sci-fi flicks, the producers of Interstellar actually made a sincere effort to adhere to scientific accuracy. So even though the movie doesn't really dive deeply into the physics of black holes, it depicts the black hole gargantua, which we see on the right here, fairly accurately. And for example, in this still image from the movie on the right, you can see kind of the bright area above left and above right of the black hole. And that's the lensing effect of the black hole's gravity lending the backside of the accretion disk. And based on what I've read, that's what you would see if you actually traveled to a black hole and view it up close. So the producers of this movie actually made a sincere effort to get a lot of the science right, which is kind of a welcome change for Hollywood. So tonight I'm going to try to dispel some widely held misconceptions about black holes. First, I'm going to point out that black holes don't roam around the galaxy sucking things in like giant vacuum cleaners. Second, they don't pose much of a danger or any danger to Earth. And third, despite their strangeness relative to human experience, black holes are actually among the simplest, most easily understood objects in our universe. In fact, they're so simple, and you can define what they are in one sentence, which I have at the upper left. And that is, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. To repeat, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. So the idea behind black holes is to cram a heck of a lot of matter into a small volume of space, thus creating a gravitational field that is so strong that even a beam of light traveling at just over 186,000 miles per second, that's not miles per hour, miles per second, cannot escape its grasp. And in fact, black holes are such simple objects that they can basically be described by just two important properties, and that would be mass and spin. And spin, of course, is self-explanatory. It's the speed at which a black hole rotates, just like, essentially every object in the universe rotates. Black holes also rotate. So mass, though, is really a black hole's most important property. It's quite simply the amount of matter that it contains. And I'm going to be speaking a lot tonight about masses, black hole masses, in terms of solar masses, which is the mass of a black hole relative to the sun. So the sun has about 333,000 times the mass of Earth. So a black hole with one solar mass has 333,000 Earth's mass. Two solar masses would be 666,000, et cetera, et cetera. And as I will discuss later, the known black holes right now range from about 5 solar masses up to about tens of billions of solar masses. Now, I want to give some historical background, and a lot of people don't know this, but the idea of black holes actually dates back to the 18th century. The first known person to suggest the possibility of a black hole was the English natural philosopher John Michell. And by applying the law of gravity as described by Isaac Newton a century earlier, Michell wrote in 1784, if the size of a sphere of the same density of the sun were to exceed that of the sun in the proportion of 500 to 1, all light emitted from such a body would be made to return towards it by its gravity. So this is a remarkably prophetic quote, pretty close to our modern conception of a black hole. Now, Michell called these objects dark stars, which is actually a good name because most black holes that we know of originated as stars. But unfortunately, he had this really great idea, and it was largely forgotten for more than a century. So our modern understanding of black holes dates to Albert Einstein, who published his general theory of relativity in a series of remarkable papers in 1915 and 1916 when World War I was raging across Europe. And I particularly like this photo of Einstein because it really shows him in his scientific prime. At the time, he was getting to be well known in the small physics community in Europe, but he had yet to achieve the global superstardom that he would later achieve. So Einstein's general relativity papers outlined a new theory of gravity that differed in concept from Isaac Newton's theory of gravitation from the late 1600s. Now, I want to make this clear. Newton's theory was brilliant for his day. There's a reason why he's considered one of the greatest scientists who ever lived, but Einstein improved upon Newton's theory of gravity. So if they're having this lightsaber battle, Einstein ultimately wins that contest. So Newton, this is a very simplified version, but Newton conceptualized gravity as an attractive force between two objects in 3 dimensions of space. And in this picture, the moon revolves around Earth because of the tugging force of Earth's gravity on the moon. So without, Earth's gravity, if Earth suddenly disappeared, the moon would fly away, like you see in that blue arrow at the lower left. But because of Earth's gravity, our planet keeps the moon locked in its orbit. And the same force then, of course, maintains Earth's orbit around the sun and that of the other planets. In this picture, space and time are separate and distinct from each other. So massive objects such as the sun have no effect on the passage of time. Okay, but in general relativity, gravity is more of an effect of mass as it warps the fabric of space, creating what I'll call a gravity well. And to envision how this works, this is like a bowling ball on a rubber sheet. And you can see how the bowling ball warps the rubber sheet at its surface and creates that depression. So this is analogous to a planet, star, or a black hole warping the fabric of space. So in general relativity, which we see on the bottom, objects move according to the distortion of space. The moon orbits the Earth because it follows the contours of the warped space resulting from Earth's gravity well, and the Earth orbits the sun because it follows the warped contours of the warped space resulting from the sun's gravity. And also in general relativity, and this is really important for black holes, is time becomes a dimension because a massive object such as a planet, a star, or a black hole not only warps space, it also slows down the passage of time in its vicinity. So as you're going to be hearing a lot tonight, it's more accurate to speak of warped space-time, not just warped space. Now, general relativity has been confirmed again and again and again in both laboratory experiments and especially in astronomical observations. And a lot of people don't realize this, but your GPS receiver that you use to navigate around the crazy roads around Boston are actually, you're doing an experiment in relativity, because your GPS would not give you accurate directions were it not for the fact that the GPS system corrects for relativistic effects. So for example, a GPS satellite's clock is in orbit. So it's operating in slightly weaker gravity than a clock on Earth. So time passes about 45 microseconds per day faster on the satellite than it does on Earth. But the satellite's clock is moving faster relative to a clock on Earth. So the GPS clock runs about 7 microseconds per day slower than a clock on Earth. So the net effect is that clocks run on the satellite by about 38 microseconds per day, which would increase GPS inaccuracy by about 6.5 miles per day. And it actually turns out that in less than an hour, your GPS receiver would become totally useless for precise driving directions were it not for the fact that computers autocorrect for these relativistic effects. So next time you use GPS, just remember you're sort of doing an experiment in relativity. Now, Earth's gravity produces slightly warped space-time, but a black hole is on a totally different dimension here. Its gravity is so extreme that it produces infinitely warped space-time. So the space-time inside a black hole is so warped that even a beam of light cannot climb out of the steep gravity well. Another way to think of this is that the velocity needed to escape a black hole's gravity is greater than the speed of light. So the boundary of no return from which nothing can escape is called the event horizon. So that anything, and that can be matter or light or your car or whatever, anything passing through the event horizon is trapped forever. And according to general relativity, that material will ultimately fall all the way down to the center of the black hole, where it will be crushed out of existence. This central point is known as a singularity, and it's a region of space with zero volume and infinite density, a place where our known laws of physics break down. So we really don't understand what happens deep inside a black hole. Now, here's a more traditional way for lay people to envision a black hole. We see the outer boundary is the event horizon. And according to relativity, at least, all the matter is concentrated in the singularity. There are other theories like string theory that give you a different internal structure of the black hole. But in the picture of relativity, this is basically it. Black holes are actually incredibly simple objects. Now, the distance from the singularity to the event horizon is known as the Schwarzschild radius, after the German physicist Karl Schwarzschild, who calculated this distance shortly after reading one of Einstein's relativity papers. I mean, this is when hardly anybody in the world even knew about relativity, and he was already doing this brilliant calculation that's still used to this day. Now, sadly, he died shortly thereafter from disease while serving with the German army on the Russian front in World War I. Now, interestingly, even though Einstein's own equations predicted the existence of black holes, Einstein himself didn't believe that such absurd, ridiculous objects would actually exist in nature. But other scientists like Schwarzschild and others took this theoretical possibility seriously. And one of them was John Wheeler here. Now, because the relativity predicts that powerful gravitational forces at the event horizon essentially freeze the passage of time, physicists were calling these objects frozen stars to refer to gravitationally collapsed stars. Well, in the 1960s, Wheeler, who was a real expert in relativity, coined the much catchier term of black holes, and that's the name that has stuck ever since. So we can owe the name black holes to John Wheeler, who, by the way, served, as one of the scientists on the Manhattan Project. Now, a fun thought experiment is to compress the sun in your mind or in a calculation to smaller and smaller sizes and see when it would collapse into a black hole. Now, the sun's actual radius is 432,000 miles, about 110 times that of Earth. But to turn the sun into a black hole, you would have to cram its entire 333,000 Earth masses into a sphere with a radius slightly less than 2 kilometers or 2 miles. That's when its escape velocity would surpass the speed of light. And if you're wondering about Earth, you would have to compress it into about the size of a marble for our planet to become a black hole, which obviously is something we don't want to see happen. And for the moon, you would have to compress all of the moon's gravity into about the size of a grain of sand for the moon's to become a black hole. Now, I've already dispelled the myth that black holes are complicated objects. The next myth I want to dispel is that black holes, roam around the galaxy and the universe, sucking in matter and light like giant vacuum cleaners. So if there's one thing I hope you remember from this talk, it's this, and that is that black holes are not cosmic vacuum cleaners. In fact, much of the matter that comes near a black hole gets deflected by the black hole's gravity. It can change speed and direction, but it's not sucked directly into the black hole. It doesn't go in, at least not immediately. It's more accurate to say that matter falls into a black hole, not that black holes are like vacuum cleaners that suck up matter. So what's different about black holes is that once matter and light fall into a black hole, it cannot get out. So it's sort of like, they're like an astronomical Las Vegas. There's the old saying, what happens in Vegas stays in Vegas. And by the way, my nephew lives in Las Vegas. What happens in a black hole stays in a black hole. And it was actually, as Stephen Hawking discovered in the 1970s, however, the situation's actually a little bit more complicated than that because of the effects of quantum physics, but that is well beyond the scope of my talk tonight. So for the purposes of our talk tonight, what happens in a black hole stays in a black hole. Now, in fact, most of the material that comes close to a black hole does not fall directly in. Instead, the material settles into orbit around the black hole. And if the black hole's, a lot of material is flowing toward the black hole, you can get a lot of material in what's called the accretion disk. And this very nice illustration shows the actual physical structure of an accretion disk, but it does not depict the gravitational bending of light that we saw earlier with some of the other illustrations of black holes. Now, this is a really, really cool animation. I love this animation. The constant collision of the gas and dust particles within the accretion disk creates friction, which causes the material to spiral inward, which you can kind of see in this video. And the material swirls around the event horizon faster and faster as it gets closer and closer. And just outside the event horizon, the material is whipping around at nearly the speed of light. And as this material is whipping around at incredibly high speed, it's generating a torrent of light like radio and X-rays. So these can be bright objects that astronomers can detect with their telescopes. So it's this process that enabled astronomers to detect black holes decades ago. And black holes are otherwise invisible objects that don't radiate any light, but we've actually known about black holes, for many, many decades. Now, one of the first black holes that astronomers detected is called Cygnus X1, and it's depicted in this idealized piece of art that shows the physical structure of the system. Now, Cygnus X1 belongs to a class of black holes known as stellar mass black holes because they have masses within the range of star masses. Now, black holes in this category range from roughly 3 solar masses to roughly 100 solar masses. And Cygnus X1 is in a binary system. So on the left, we see the black hole with about 20 solar masses, and it's surrounded by its accretion disk. And on the right is an extremely hot blue supergiant star that contains about 30 solar masses. Now, the two objects they orbit around the common center of gravity. They're very close to each other. About the average distance is about 1/5 Earth's distance from the sun. So that's, very, very close. What's interesting here is that the center of gravity is actually closer to the star than it is to the black hole because the star is more massive than the black hole. Now the star, it's a blue supergiant, it's giving off a very powerful wind of gas. And a lot of that wind, if it's kind of sent off in the direction of the black hole, that material is going to end up in the accretion disk. It's going to spiral in, radiate X-rays that astronomers can detect. So that's how we detected Cygnus X1. So this is actually a more accurate rendering of what we would see if we could view Cygnus X1 up close. The black hole is rendered more accurately with the lensing effect that I mentioned earlier. And the star itself is tens of thousands of times more luminous than the sun. So it would be like incredibly, blindingly bright if we viewed it up close. Now, astronomers discovered the star long ago. In fact, I bet you a lot of you on this Zoom call have probably seen it in a telescope, whether you've known it or not, because it's about 9th magnitude. But in December 1970, astronomers launched the Uhuru satellite, which we see on the right, to detect bright X-ray emitting objects in space. And Uhuru very quickly found this very bright X-ray star or X-ray emitting object at the same coordinates as this blue supergiant star. And astronomers then realized from the star spectrum that it was being tugged and orbiting a companion object that had a fair amount of mass, but that object was invisible. Okay, it's invisible. So this star is in orbit with a very massive object that's not emitting any light, but then you have all these X-rays coming from the system, and they figured out pretty quickly that the X-rays are probably coming from a disk around a black hole. So this is a way that you can see a black hole. You're not seeing the black hole directly, but you can observe the black hole's influence on the surrounding environment. So Cygnus X1 was the subject of a well-publicized wager between British physicist Stephen Hawking and Kip Thorne at Caltech, who I mentioned earlier was the scientific advisor for the movie Interstellar. So not long after Uhuru detected X-rays from Cygnus X1 in the early 70s, most astronomers, including Kip Thorne, quickly concluded that the system contains a black hole. Now, Hawking also thought it contained a black hole, but because he wanted it to be a black hole, he decided to hedge his bets and made a wager with Thorne in 1975 that the system does not contain a black hole. Now, in 1998, the astronomical evidence in favor of a black hole in Cygnus X1 and black holes in general became so compelling that Hawking conceded the bet and Kip Thorne won the bet. And so Hawking wrote, quote, "I paid the specific penalty, which was a 1-year subscription to Penthouse magazine, to the outrage of Kip's liberated wife." So until very recently, all known stellar mass black holes existed in binary systems, essentially in partnership with a star. But less than 2 weeks ago, a large international team of astronomers, which included amateur astronomers, some of whom I've met in New Zealand, announced compelling evidence for the first known isolated stellar mass black hole in our Milky Way galaxy, meaning it's a black hole without a binary companion. So this slide shows a beautiful artist's rendering of an isolated black hole that is accreting little or no matter. Now, this is an exciting discovery because isolated black holes, by their very nature, are exceedingly difficult to detect because they're not radiating any light. So the newly discovered black hole has about 7 solar masses, so it's a fairly small black hole, and it lies about 5,000 light years from the sun. The team discovered this black hole using a technique known as gravitational microlensing. Now, the Scientific America's website had a very nice write-up of this discovery about a week ago, and I sent the link to Mike. So if you're interested in more of the details, you can either email Mike or you can email me, and we can send you the link to the story. Or if you want, you can ask me to give more details in Q&A. Now, astronomers worked out long ago how these stellar mass black holes form. Specifically, they are the end products of evolution of extremely massive stars, those that start their lives with roughly 30 or more solar masses. Now, these are extreme and very rare stars. They're less than 1% of the stars in our Milky Way galaxy. And these very massive stars are like the rock and roll stars of the 1960s, like Jimi Hendrix or Jim Morrison. They live fast and die young. Now, the evolution of stars is complicated, could easily be the subject of its own GAAC talk. But to make a very long story short, massive stars burn through their nuclear fuel extremely rapidly. That's why they're so luminous. and only a few million years, they're done. They're at the end of their lifetime. And so, for example, the sun is going to live for 10 billion years, which is about 1,000 times longer than the lifespan of the stars that form black holes. So when these massive stars run out of fuel on their cores collapse, and you get a big bang known as a type 2 supernova that blasts away the star's outer layers. And if the collapsing core of the star has roughly 1 to 2 solar masses, the collapsing core will form an ultra-dense stellar cinder known as a neutron star, which is roughly the size of a large city like Boston. But if the core has 3 or more solar masses, gravity will overcome all the other forces of nature and will collapse the core all the way down to a black hole. So these black holes that form from stars contain about 3 to maybe roughly 50 times the mass of the sun, which means they're, like 2 to 5 miles across. But then there's another major class of black holes, and these are the monsters of the universe. These are known as supermassive black holes. And every large galaxy, including our own, appears to harbor one of these beasts at its center. Now, there are roughly 100 billion galaxies in the visible universe. So we're talking on the order of 100 billion of these supermassive black holes. Now, these monsters range from tens of thousands of solar masses up to several tens of billions of solar masses. So whereas stellar mass black holes are only a few miles across, a supermassive black hole has roughly the diameter of our solar system. Think of it out to the orbit of Neptune and Pluto. Now, the known record holder for a supermassive black hole is in a galaxy called TON 618, and it has a mass of, this is staggering, 66 billion solar masses. Now, these giant black holes are incredible objects, but when you think about it, they still only contain about 1% of the total mass of their host galaxies. So the combined stars and dark matter and interstellar gas clouds still vastly outweigh the black hole at the center. But of course, the black hole is by far the most massive individual component of the galaxy. Now, these monster black holes are usually surrounded by these accretion disks. Some of them are huge, and this creates an incredibly powerful engine where truly extraordinary things happen. There's magnetic fields that are being wound around by the black hole is spinning rapidly. You get material whirling around the disk at incredibly high speeds, and all of that creates these magnetic fields that get wound around kind of like stripes on a barber pole, and it just whisks away electrically charged particles and funnels them into these jets that shoot away in opposite directions from the black hole at speeds nearly that of light. And here we see, I think this is a really, really nice artist rendering of this process. Now, I want to be clear here, the details of this process are not yet fully understood. There's a lot we don't know about exactly how this works. But you can see here that the material can get fairly close to the black hole without falling in. And as I just explained, some of this material is not going to end up in the black hole. It's going to end up in these jets and shoot away from the black hole. So this stuff will escape the black hole. Now think for a moment about the Death Star in the Star Wars movie. Now in the movie, these planet-shattering beams look really fearsome, but they don't really give us measurements, but they're traveling maybe a few 100,000 miles at most. And that looks impressive on a movie screen, but compared to these black hole jets, the Death Star beam is really quite pathetic. Some of these monster black holes produce jets that stretch across space for hundreds of thousands of light years. That's actually greater than the distance from one side of our Milky Way galaxy to the other. That's a vast expanse of space. And the energy in these jets vastly exceeds the Death Star planet-destroying beam. Now, this is an image from a radio telescope of two jets shooting away from a monster black hole in the center of a galaxy called Cygnus A. And the jets eventually slam into interstellar gas clouds, creating the lobes of radio emission we see at the lower left and upper right. The jet on the right is sort of aimed a little bit more in the direction of Earth, so it appears brighter. The other jet's moving a little bit away from the direction of Earth, so it appears dimmer. That's a beaming effect actually predicted by general relativity. And here's a very dramatic Hubble Space Telescope image of a jet shooting away from a giant black hole at the center of the giant elliptical galaxy M87, which is in the Virgo cluster, about 50 million light years from Earth. Now, the visible part of the jet in this image is about 5,000 light years in length, which actually is kind of small compared to the jet I showed you from Cygnus A. And I'm going to return to this black hole in just a few minutes. Now, besides the jets, the accretion disks swirling around the supermassive black holes can generate very powerful winds of hot gas that blows away from the black hole. So there's a lot of stuff that's not going to fall into the black hole. Such active centers of galaxies are often called quasars, and these quasars can outshine the many billions of stars in their host galaxy. So the energy coming from these objects is staggering. Like there's more energy coming from these quasars in 1 second than our sun will radiate in its entire 10 billion year lifetime. So quasars are the most luminous, continuous sources of energy in the universe, and they can be observed at distances of 10 billion or more light years. So, by providing all of this energy and these jets and wind, these monster black holes can have very powerful effects on their surroundings. So you might be wondering what about the black hole at the center of our Milky Way galaxy? Here's an infrared image, a wide field image, looking toward the center of the galaxy, showing individual stars as points of light, and kind of the colorful, reds and blues are interstellar clouds. And you can see on the lower right an arrow pointing to a bright region. That's the center of our Milky Way galaxy, located about 25,000 light years from Earth, and it's in the direction of Sagittarius. It's kind of to the upper right of the teapot. And at the very center of that bright area there is a moderately bright radio and X-ray emitting object known as Sagittarius A star. And this is going to be a G-rated movie. If there's any kids or parents with kids, don't have to worry about your kids watching this movie. This is a movie now showing the motion of stars orbiting around Sagittarius A star, which is that white star in the center. This movie was taken over 25 years by a research group at UCLA led by Andrea Ghez. Now, this movie was made possible by extremely advanced technology on the Keck telescope called adaptive optics that I can discuss during the Q&A if anyone's interested. It essentially enables astronomers to correct for the distorting effects of Earth's atmosphere. Now, These objects are moving at high speed. Remember, this is over 25 years. And to keep, and notice the yellow one, that's the star SO2. To keep these objects locked in orbit at these high speeds, the central object must have a mass of about 4 million times the mass of the sun. So what we have here is at the center of our galaxy, we have a supermassive black hole with a mass of about 4.5 million times the mass of the sun. And I should say that, point out too, that the motions of the stars are beautifully obeying the predictions of general relativity. Now, the central region of our galaxy right now is relatively quiescent. There's a little bit of radio and X-ray emission coming from the black hole's vicinity, but there's no clouds right now, or no stars that are right now being accreted onto the black hole. So, the black hole at the center of our galaxy is kind of a hungry monster right now. It's basically, it's desperate for a large meal. And I want to mention that for this groundbreaking research, GAAC shared the 2020 Nobel Prize for Physics with the German astronomer Reinhold Genzel, whose European research team did essentially the same work and got essentially the identical results, seeing the same stars in the same orbit, getting the same measured mass for the black hole. So if you think GAAC is wrong, well, then you got, Genzel would be wrong too. Much more likely they're both right. They basically confirmed each other's work. And they shared the Nobel Prize with the great British physicist Roger Penrose, who was a longtime friend of Stephen Hawking, whose theoretical research helped pave the way for our modern understanding of black holes. So I was really, really excited when I got the news that these three great scientists won the Nobel Prize for basically astronomical work. Now, it remains a mystery of how these black holes formed. Astronomers can see them, these quasars, at immense distances, which means we're seeing them all the way back to the time when the universe was very young. They've even found quasars that were shining brightly when the universe was less than 1 billion years old. I mean, it was still basically a toddler. So there must have been some process in place in the first billion years of the universe's existence that concentrated large amounts of matter into a very small volume of space to form these monster black holes. And I actually wrote a cover story for the March 2021 issue of Astronomy magazine that looked at a couple different theories. And I would argue that one of the great astronomical discoveries over the past 20 years is the fact that the masses of these monster black holes are very tightly correlated with the masses of the host galaxy's central region. So kind of, in short, the bigger the galaxy, the bigger the black hole. And this is very powerful evidence that the evolution of the black hole is intimately connected to the evolution of the host galaxy. So even though the black hole is only a tiny percent of the galaxy's volume and only 1% of the galaxy's mass, these jets and outflows that I described earlier, are affecting material at very, very large distances from the black hole. So these black holes are affecting star formation and galactic evolution tens of thousands of light years away from the black hole itself. Now, I'm going to go through this quickly because your speaker next month is going to be talking about the Event Horizon Telescope, but I'll give you a little bit of a sneak preview of next month's speaker. I'm sure many of you remember in 2019, this made international global news, was what was touted as the first picture of a black hole. Now, in truth, the black hole is, or the image is not showing the event horizon. It's basically showing the shadow of the black hole surrounded by a ring of hot gas, which is basically the accretion disk. Now, this image is an amazing technical achievement made by precisely combining the observations of 8 radio telescopes. You can see them on the left here around the world, taken over several days in 2019. This technique is called interferometry. The black hole is at the center of the galaxy M87. I showed the jet just a few minutes ago, the Hubble Space Telescope image. And this black hole contains a whopping 6.5 billion times the mass of the sun. So it is, it's, roughly 1,000 times more massive than the black hole in our galaxy. And we see the team leader here on the right, Shep Doeleman of MIT, who is a team leader of the Event Horizon Telescope. I won't be surprised if someday he wins the Nobel Prize. Now, at the upper left is a simulated image from the Event Horizon Telescope that when I was editor-in-chief, we published this image in 2012. My colleague at the time, Camille Carlisle, wrote a cover story about what the Event Horizon Telescope was going to see. Now, compared the predicted image to the actual images at the right, taken over a period of several days, and you can see that the prediction was pretty much spot on, which once again is telling us that general relativity is giving us a very accurate picture of what's going on around black holes. The southern part of these images are slightly brighter because that's where the accretion disk is flowing toward us. And, and once again, that's a beaming effect. And you can even see day-to-day changes resulting from changes in the accretion flow around the black hole. And now I want to move on to an incredibly exciting new method for detecting and studying black holes. Now, astronomers have long suspected that some black holes, just like stars, pair up with another black hole to form a binary black hole system. And this would be true of both stellar mass black holes and supermassive black holes. And this is a beautiful illustration that we see of a pair of stellar mass black holes that are locked into orbit around each other in a binary system. And here you get to see another movie, again, rated G, no sex or violence. So as the black holes rapidly orbit a common center of gravity, general relativity predicts that their extreme gravity and fast motion combine to produce powerful ripples in the fabric of space-time. These are like ripples emanating from a rock thrown into a pond. These ripples are known as gravitational waves, which are basically depicted in this animation. And these gravitational waves carry away orbital energy from the binary system. So it causes the two black holes to draw closer and closer. Every orbit, they get a little bit closer until they eventually collide and merge. And here we see another very nice simulation showing the two black holes orbiting each other and eventually merge. And this is more how this would appear to the human eye. But note that in real life, this process would be happening at a much faster speed. Everything in this video would be taking place in less than 1 second. So this video, though, does do a good job of showing how the gravity of the black holes distort the pattern of background stars and gas clouds. Actually, I'll let you look at it one more time, and we're getting close to the end here. A few more slides. Once again, you see the distorting effects here. This was an attempt to actually render this accurately. And you see the black holes are getting closer and closer and closer. And then they're about to go bang and merge, wobble a little bit. That's called the ring down. And then you get the merged black hole. Oh, by the way, one of the contributors to this video, Oberlin College, that's my alma mater. These LIGO astronomers have discovered thousands of black holes by detecting their effects on the surrounding environment, as I've described earlier. But over the past 7 years, scientists working for the US LIGO laboratory and Europe's Virgo lab in Italy have detected new black holes by catching gravitational waves from their in-spirals and mergers. Now, this is the LIGO Observatory in Livingston, Louisiana. There's a near twin in Hanford in Washington State. And recently, another observatory just opened up in Japan called Kagra. Now, since LIGO's first discovery of gravitational waves from merging black holes in 2015, it has detected gravitational waves from a total of about 90 mergers, which are plotted here on this chart. About 85 of these 90 mergers, so almost all of them, are from two black holes merging. And these are black holes that are stellar mass black holes. LIGO has also detected 2 mergers from neutron stars colliding and 3 mergers in which a black hole swallowed a neutron star. Now, some of the black holes here, and the masses are plotted in these little squares, are surprisingly massive, with 50 or more times the mass of the sun. And just recently, the Virgo and LIGO team members announced the most massive binary black hole merger yet. And you can see it go to the second row, 1, 2, 3, 4, 6 over from the left. When I learned of this, I was just blown away. These are black holes with a whopping 107 and 77 solar masses, which merged to produce a black hole of 175 solar masses. So this is really interesting. This newly created black hole falls well into a category called intermediate mass black holes, which have roughly 100 to 10,000 solar masses. Now, not many black holes have been found in this mass range, but the LIGO and Virgo results prove that these intermediate black holes exist in nature. They're sort of in between the stellar mass black holes I talked about early on and the big supermassive monsters I talked about later. Now, a major open question is how black holes with many tens of solar masses come into existence, because collapsing stars are not thought to be able to produce such massive black holes. So scientists think that this new class of 50 to over 100 solar mass black holes are themselves products of smaller black holes, pairing up in binaries. They in-spiral and merge, then maybe gravitationally they lock onto another black hole that eventually in-spirals and merge. So you can build up a black hole from like 10 solar masses up to like 50, 70, 80, 100 solar masses. This process could be happening like in the cores of dense star clusters, or another idea that's depicted, I think this is a really incredible piece of space art, is that this could happen frequently in the accretion disks of supermassive black holes. So in this artwork, at the upper left, you see the supermassive black hole at the center of a galaxy. And then at the lower right, you see 2 black holes that are lower in mass, stellar mass black holes in the accretion disk they're going to be rapidly accreting matter from the disk, and then the gravitational wave emission will drive them together where they will then merge. So we might be seeing signs of two black holes merging in the accretion disk of a supermassive black hole, which is really, really, I mean, if that just blows me away. So I also want to just quickly mention that the LIGO and Virgo detections are giving scientists a really golden opportunity to test relativity in very, very high gravity conditions. And there was just a webinar run by the science team out of with Caltech and other astronomers about a month ago. So far, relativity is passing every test that black holes can throw at it and that LIGO can detect. So these LIGO discoveries are just groundbreaking. And I've actually given entire talks devoted to LIGO and gravitational waves. In fact, Mike emailed me earlier today and said that I gave a presentation to GAAC 6 years ago tomorrow on February 12th, 2016. So I've actually already talked to your club about LIGO and gravitational waves. Now, the LIGO team has more than 1,000 scientists in the US, but in many countries all over the world. As I said, we have a scientist from working in Australia. This is a global, beautiful, wonderful global collaboration. But they decided when the first one was announced in 2015, the first event, they had to give a Nobel Prize. The committee only gives it to 3 people at most. So they gave the Nobel Prize, and I think correctly so, to Rainer Weiss of MIT on the left, and then Barry Barish and Kip Thorne of Caltech, who we see in the center and right. And of course, we've seen Kip Thorne earlier for his work on the movie Interstellar and with his bet with Stephen Hawking. So this was obviously an extremely well-deserved Nobel Prize, but it's kind of a pity that more members of the team couldn't win the Nobel Prize. Maybe there'll be few discoveries in the future that members of the team will win a Nobel Prize. Now, I want to conclude by discussing whether you should be afraid of black holes. After all, they have frightening characteristics. So could one come close enough to Earth to rip it apart, to kind of tidally rip our planet apart, as depicted in this illustration? Now, a recent paper, this came out just about a month ago, by mostly Italian and British physicists, estimate that there are about 40 billion black holes in the observable universe. So some people might be, oh my God, there's enormous numbers of black holes. Are we in trouble? I mean, that's a lot of black holes, but almost all of them are in extremely distant galaxies. So there's nothing to worry about. The only ones that concern us are those that are in our galaxy, and even more specifically in our own galactic neighborhood. Now, it is theoretically possible that Earth could be destroyed by a black hole, but there are many other things you should worry about more. Now, you might be thinking, what about our supermassive black hole at the center where I showed that movie earlier? It's 25,000 light years away, way too far away to pose any threat to our planet. Now, the closest known stellar mass black hole candidate is about 1,000 light years away, but even that is way too far away to pose any kind of threat. We don't know of any black holes that are really close by. The best guess is that there are about 100 million stellar mass black holes in the galaxy. That seems like a lot, but the galaxy is so enormous that the closest black hole to Earth right now is probably many tens or even several hundred light years away. And that's still way too distant to pose any threat. So if a black hole did wander into the inner solar system, however, that would be very bad. Now, it's very unlikely it would come close enough to Earth to like gravitationally destroy our planet. But the biggest danger would come from the fact that its powerful gravity would throw the Earth and all the planets out of their orbits. The Earth is in a near circular orbit. We'd be yanked out of that orbit into probably thrown away from the sun. So if we're thrown away from the sun, we freeze to death. If we're put on a trajectory where we get closer to the sun, then we boil to death. This is a wonderful piece of space art, but it really does not depict a scientifically plausible scenario, and certainly nothing that any of us need to worry about. I also want to point out that our galaxy has about 200 billion stars. So there are several thousand stars for every black hole in the Milky Way galaxy. So if something is going to come into the inner solar system and start throwing planetary orbits out of whack, it is much more likely to be a star than a black hole. But, we've been around, Earth has been around for 4.5 billion years without having been disturbed by a marauding star or a black hole. So I think this is telling us that the danger from black holes is practically zero. I'm actually a lot more worried about people like Vladimir Putin than I am about black holes. But if you were to travel in a spaceship to a black hole, you better be really careful. It's not something I'd really advise you to do. If a black hole is accreting large amounts of matter and generating powerful winds and jets, that radiation would be incredibly dangerous, and you need a hell of a lot of shielding or the radiation would kill you. But let's say the black hole's not accreting much, not generating much of a wind or radiation. And if it's a stellar mass black hole, if you start getting too close, you will experience extreme tidal forces. Remember, this object is, only a couple miles across. And as you get closer and closer, it's the force of gravity that it's exerting on your feet, if you're going feet first, is going to be enough stronger than the force at the other end of your body, at your head, that you're going to be tidally stretched into a strand of fleshy spaghetti. So you would die of a process known as spaghettification. Doesn't sound like a very pleasant way to go. So I would recommend not getting too close to a black hole. And believe it or not, the term spaghettification is an actual scientific term describing this process. Now, you would actually be much better off approaching a supermassive black hole as long as it's not accreting large quantities of matter. Because of the black hole's greater size and more powerful gravity, the gradient of its tidal forces are more gentle, meaning you could actually cross the event horizon while you are still alive, but you'd still eventually get crushed gravitationally crushed as you approach the singularity at the center of the black hole. So ultimately, it's still a one-way journey, not the way I would recommend you go to meet your, if you're going to commit suicide, there's better ways to do it. I want to wrap this up with some wild speculation, but fun speculation. As I've explained, you don't want to get too close to a black hole, but black holes can be these immense sources of energy. So scientists and science fiction authors have proposed the idea that highly advanced civilizations, those with technology way beyond our own, even more advanced. I know Mario won't believe this, but even more advanced than his 32-inch telescope, these civilizations could get just kind of the right distance from the black hole, where they can tap into the rotational energy and some of the, the energy coming from the accretion process, but far enough away that they're safe. And they could build space colonies there that would have this enormous and, seemingly inexhaustible supply of energy. So astronomers have actually suggested that we observe black holes for technosignatures, which are, signs of advanced extraterrestrial civilizations. So, I'm skeptical that we'll ever find a technosignature near a black hole, but who knows? I don't think it does any harm to look. So I want to thank you all for your attention. To stay within my allotted time, I actually probably did go over a little bit. I didn't discuss a lot of really interesting topics related to black holes, such as the possibility of primordial black holes, the possibility of creating tiny black holes in a laboratory, the information paradox, and stuff like wormholes. So feel free to ask me about any of these topics or anything else. And in the meantime, these are 4 books that I very highly recommend. They go from the least technical on the left to the most technical on the right. I should mention the book on the left, Marcia Bartusiak. It lives in Massachusetts. I think she lives in Sudbury. Chris Impey is at the University of Arizona. I talked about Kip Thorne earlier. He's at Caltech. That's a phenomenal book, but it's a little bit technical. And then this information paradox is the subject of the book on the right. And Leonard Susskind is at Stanford University. So thank you all very much. And I'll end the show. I will stop sharing and we can take questions. And
Bob, I always thought spaghettification was eating way too much pasta at one sitting.
Yeah. Well, I actually ate, let's see, I forgot how to stop the screen share.
I can take care of that for you, Bob.
Okay. Yeah. I actually ate spaghetti for lunch today, knowing I was giving the talk tonight, and I probably ate a little bit more than I should have. And I actually hardly ate anything for dinner because I had such a big spaghetti lunch today.
I think it's what happens when people get ready for the Boston Marathon and they have a little too much.
Yeah, that's right. Yeah. Well, with the energy from that spaghetti, maybe I could have run the Boston Marathon. Not that I've ever tried to run 26 miles.
Before we get started with the questions, I just want to tell everyone that when I send out the link to the recorded presentation, I will also send out a couple of links that Bob mentioned and that he sent along. So you'll get those in the same email. A conservation of emails. Good principle. All right. There was one question that was in the chat very recently about, if I'm interpreting it correctly, why on earth would we create these terrible monsters on Earth if we could?
Okay. So no, I'm really glad someone asked that. So here's the deal. There's these various theories like string theory that predict extra dimensions. And I actually wrote an article about this years ago, but I forgot all the details or most of the details. And according to these theories, you could have a particle accelerator that would, you would actually, that means that gravity is actually stronger than we think it is, but it leaks out, its strength is diluted by these extra dimensions predicted in string theory. And so you could take, say, a large particle accelerator like the Large Hadron Collider in Switzerland. And if you're slamming, let's say, subatomic particles together at almost the speed of light, if you can get them up to enough energy, you will create these tiny black holes. Now, these black holes are, I don't remember exactly what the mass is, but it's like the mass of an atomic nucleus. These are incredibly tiny black holes. And based on the quantum processes that I mentioned briefly in the talk, and that Stephen Hawking described in the 1970s, these black holes will instantly evaporate. So they would be created in the lab, but before they could do any harm, they will instantly basically disintegrate. And you can argue, there's some people who said, well, we still shouldn't do the experiment just in case, but the theorists have a good comeback to that. And that is that, like, all the time, cosmic rays, which are, charged particles or atomic nuclei, are slamming into Earth's atmosphere at nearly the speed of light. And some of the highest energy cosmic rays, things that are happening all the time, are hitting the Earth and the planets, the sun, all the time at much higher energies than we could ever create in the laboratory, or at least not for a very, very long time into the future. So nature, if these theories of black hole creation are true, then nature is constantly creating black holes in Earth's atmosphere. Like every day, it's happening many times every day. So Earth hasn't been turned into a black hole. So therefore, it is safe to do these experiments, because even if they do create black holes, the black holes will just instantly evaporate before they can start gobbling up matter and doing any harm. So I believe that that is a very good argument, a valid argument, and that these experiments are safe to do.
Okay. In addition to a lot of compliments on the talk in the chat, there's a question from Bill Waller on singularities. Bill, you want to ask that yourself? You're on mute.
Yes,
There you go.
yeah.
Hey, Bill.
Hi, good to see you. Wonderful presentation.
Thank you.
The thing about the singularity, it's so heinous, in that it's infinite density, zero radius, infinite density, that it's shunned by most self-respecting physicists.
Yep.
And so I'm just asking, is there a way to avoid them? Also, if there's any evidence for these singularities, because they're all embedded inside these event horizons, these horizons of unknowing. And and the third possibility is, does it even matter with space-time getting so scrambled? Would you even know whether or not you have infinite density?
Yeah, no, those are all great questions, and you're sort of taxing like at the limits of my knowledge of this very complex physics. What I can say though, and I've certainly edited and written articles for Astronomy Magazine and Sky and Telescope, there are theories like with string theory that can avoid the singularity, that you have internal structure to the black hole, and that you avoid, as you said, like this very egregious, kind of violation of physics where you have, a point of zero volume and infinite density. I'm not really that knowledgeable about that.
Mm-hmm.
I tend to be very skeptical of string theory. I think it's sort of like astrobiology. It's a field of physics whose subject matter has not been proven to exist. So I tend to be skeptical, but I've talked to a number of scientists from the books and articles I've read. There does seem to be a view that somehow, some way, nature I think there's a statement, nature abhors a singularity. And so there's a thinking that we haven't, for example, unified yet quantum mechanics and general relativity. Both theories are brilliant, but they don't play nice together. And that if we could ever develop a theory of everything, whether it's string theory or loop quantum gravity or whatever, there will be a way that nature will find a way to avoid a singularity. Whether we could ever observe that, given that whatever's inside a black hole is hidden behind the event horizon, I don't know if we'll ever be able to observe it. If there's ever a theory that really gains widespread acceptance, that kind of merges relativity and quantum mechanics, it could make predictions of things that we can observe. Like maybe like LIGO will start seeing in certain circumstances, we're getting slight deviations from what relativity predicts. And this new theory would predict that. And if it predicts new phenomena, then it would give physicists confidence that if it's predicting some kind of structure inside the black hole, you would have confidence that that theory is probably correct or more correct than relativity. But even if you can't actually test it experimentally. I've also read, there was an article a few years ago in Scientific American about naked singularities, like singularities without event horizons. I have to be honest, I read that article and I really didn't, it was written at a very high technical level. I usually have no problem understanding Scientific American articles. They're usually written at a level that I can understand. But that article, I really didn't get it. And I don't know if anybody else read that article and got it. But it was an article about how naked singularities could exist in nature. But I didn't understand. Let's just say this, I didn't understand it well enough that I remember it, can speak intelligently about it to you tonight.
Okay, good, thanks.
Yeah, thanks for the great question, Bill. Good to see you again.
Any other questions for Bob?
This is Al Ryan.
Hey, Al, how you doing?
Hi, Bob. Great presentation. And thanks to Gloucester for allowing me to chime in here. I guess I have a simple question because I'm a simple person. On your LIGO chart with the merging black holes,
Yep.
there was less mass in the resultant in the merged black hole. And can you just tell me what form that extra solar mass took? And also, would these black holes have different spins, and would that somehow be conserved or accounted for in the resultant black hole?
Yeah, no, those are great questions, Al. And by the way, Al now has an observatory named after him, the Al Ryan Observatory. He helped found this really wonderful amateur observatory in Lancaster County, Pennsylvania. I did a write-up for it a couple of years ago for Sky and Telescope, and they're about to add, I guess, a new binocular telescope, correct?
That's correct. I think it's the largest binocular telescope specially designed for public use.
Okay, great. And I can't wait to get down. It's only less than an hour drive from where I live, so I want to get down there and look through your telescope maybe once the pandemic is kind of subsided. In any event, to get to your questions, though both are great questions. And I thought about mentioning it during the talk, but I just wanted to keep going and not go much over an hour. What happens is when you have two black holes merge, the gravitational waves actually carry away some of that. Remember, the E equals mc squared, there's an equivalence between mass and energy. So as the gravitational waves are carrying away orbital energy, they're actually carrying away mass, so that the merger of the two black holes, you get slightly less than the mass of the adding the two black holes together. So for example, if you get like a 50 and a 60 solar mass black hole, instead of ending up with a 110 solar mass black hole, you might end up with like 105 solar mass black hole. So that's why the product, and you were very eagle-eyed to catch that, that's what happens. You're losing mass. So the resulting black hole is slightly less massive than the product or the sum of the two smaller black holes. And then the second question is, and this is very important, and the answer is that the black holes are spinning, and this is something, I don't know if Isabel, if she's still on the call, if she wants to go into more detail, the spin of the black hole is very significant in terms of like the time it takes to merge. You know, it has how the black holes are spinning does have a significant effect on the details of the merger, and scientists can actually get measurements from the LIGO data of how the black holes were spinning in the moment leading up to the merger. So if Isabel, if you're still on, would you like to comment on that?
Yeah, sure. So I think the specific question was about whether the spin of the two components would be conserved in the final object. And actually, it turns out that if you have two black holes that in-spiral and merge together, the final black hole will always be spinning in basically the same way, regardless of the spins of the components. So the magnitude of the spin, which is like the size of it, is always around 0.7. Regardless of what the spins were that kind of went into creating it, which is an interesting way to be able to figure out if the black hole that you're observing was already formed out of a collision of two black holes previously.
And here's a question for Isabel. From the LIGO data, what kind of spins are you getting for black holes before they merge? Like, is it like 0.9 or much slower than that? Like 1 would be the theoretical maximum, right? Where the event horizon is spinning at the speed of light. So you can never get to 1, but you can get to like 0.99.
Yeah, that's true. So we haven't observed anything that's really rapidly spinning that we can confidently say is definitely spinning like that. There are quite a few things that look like they might be spinning quite rapidly. And also that they might be spinning in a way that is not aligned with the angular momentum of the orbit, which is interesting too. So we don't really have enough detections to make confident statements yet, but we're seeing some interesting things in the spin.
And I would think too, with your sensitivity continues to get better and better. So you're sampling out to a greater volume of space. So like the event, I mean, I remember when every new detection was like in the news, it was a big deal. And now it's like, you guys don't even release it until you have like a dozen new detections. So I would think in the coming decade, we're going to get up to hundreds and hundreds and hundreds of events with lots of different masses and mass ratios. So you're going to learn a lot more about spins in the coming decade. Is that correct?
That's definitely true. Yeah. And also once we have kind of hundreds and hundreds of detections, we'll be able to make population statements about like what the population in general is looking like in terms of the spin properties, which will tell us how these things are forming in the first place, which will be very exciting.
Yeah, that's something astronomy. I mean, it's kind of interesting because LIGO, I see it as more of a physics experiment, but there's going to be a lot of astronomy and astrophysics coming out of it, of a population. I mean, here's the thing, like we had never seen a binary black hole until 2015. I mean, they had to be out there. I mean, but like how many are there? What are the masses? What are the mass ratios? What are their environments? They're like, this is like, these objects are effectively invisible. They have to be out there. And now we have a way to study them and really get a good handle on their astronomical populations and properties. I assume you'd agree with that.
Yeah, definitely. I think it's funny that you say that it's like a physics experiment. I think that's really true. I think it's like there's a lot of theoretical physicists who now suddenly have found themselves being observational astronomers when they never really assess how to do this. But,
Oh, wow. Okay.
Yeah.
Mario has his hand up there very patiently.
Oh, he's mad because I dissed his 32-inch telescope.
Actually, I'm not going to ask you a question. I'm going to ask Isabel a question. So there. I just want to make sure I understood you. Are you implying from your last statement that the angular momentum when two black holes merge is not conserved?
So the angular momentum of the orbit is conserved. That's what kind of leads to this final spin of the
So it is conserved.
Yeah.
Okay. I misunderstood you then. Okay, that's fine. Thank you.
I should just mention too that, and I don't remember the exact issue, but I commissioned and edited a really great article. It was a cover story for Sky and Telescope by Harvard astrophysicist Laura Brenneman about black holes and rotations, and how like the rotation can tell you about the history and the physics, because it had, you know, the rotation affects the jet formation and how close the accretion disk can get to the event horizon. Like rotation is, you know, I said in the talk that mass is the most important property of the black hole, and that's true. And I think Isabel would agree, but, you know, rotation is an important property. And so Laura's article, if any of you email me, I can get the PDF and email her article to you. It was a really, really interesting article about black hole spin. And Laura also, I don't know if any of you've met her, she's also a tremendous athlete. She played for the US women's national baseball team in international tournaments. This was not softball, this was baseball. She said she only really enjoys playing baseball and not softball. So she's a really good athlete too, besides being, you know, a really great astrophysicist.
All right, let's say 2 more questions. What's the first one? There's only 2 of them. You got to get greedy here.
No, I just want to say if Isabel had anything else she wanted to add that I didn't discuss, I'd be happy to have her chime in.
There's lots of interesting, you know, topics related to all of the things that you discussed. But I think I should let other people ask questions first.
Okay.
I have a quick question. It's only tangentially related. Al Ryan was mentioning the largest binocular telescope, and I was wondering just how large that is.
Okay, I'm told it's the largest for public use, especially designed to make it easy for people of varying interocular distances to view. Each mirror is 25¼ inches. I think, what is that, like 628 centimeters.
That's awesome. Thanks.
And when do you think it'll be operational, Al?
Well, for you, Bob, it's operational whenever you want to come out.
Okay.
We're opening it to the public probably June.
Okay.
Yeah.
That'll be great.
Great presentation, Bob. Thank you.
Yeah. Thank you.
Thank you, Isabel and Al as well.
All
Thank
right,
you for
any
letting
more
me crash
questions
your
for
meeting.
Bob?
I did have one other observation. Bob, I noticed you stayed away from the notion of information loss in a black hole.
Okay. That is incredible. No, that's fine that you asked it. That is an incredibly complicated topic, and it relates to this quantum effect that Stephen Hawking with, you know, and there were other scientists involved in the 70s, like Jacob Bekenstein from Israel and others, who realized that black holes, you know, I showed you that slide that says what happens in a black hole stays in a black hole. But I said that there, you might remember, I briefly mentioned quantum effects, and black holes do radiate away their mass. Like we see it with the mergers with the gravitational waves, but there's this process because of quantum effects that they do lose mass over time. They slowly leak away their mass. Now, I think for a stellar mass black hole, they evaporate on something like 10 to the 94 power years, and a supermassive black hole with, let's say, 1 billion solar masses, it would take something like 10 to the 100 power year. I don't remember the exact numbers, but it's an enormous length of time that they will radiate away all their mass. The question is, like, let's say a black hole came toward Earth and it was on just the right, you know, everything just works out. So it sucks Earth, you know, Earth gets tidally shredded, the material forms an accretion disk, and the material falls into the black hole, there's information like what was it, like carbon atoms, oxygen, you know, whatever, the information that made up planet Earth ends up inside the black hole. The question is, when that information, does that leak out in this Hawking radiation, this effect that Hawking predicted through quantum mechanics, where the black hole is kind of slowly shedding the mass that fell into it? Does quantum mechanics says that the information must be conserved, that the information of what fell into the black hole is somehow preserved and eventually readmitted out into the universe by this Hawking process. But then there's other physicists that say, no, the information is ultimately destroyed. It gets down to the singularity, it's crushed. So the black hole does not preserve any memory whatsoever of what fell into the black hole. So that book on the right that I showed by Leonard Susskind is about that debate within the scientific community about whether black holes do or do not preserve information about what fell into them. Did I describe that properly, Isabel? And do you have any thoughts on that?
Like, information loss in black holes is not something that I know a great deal about, so that was news to me. So,
oh, okay. I know it's
I'd
really
rather
weird.
believe in a singularity than Moby Dick popping out of an event horizon.
That's right. Yeah. So I don't know where the debate stands right now. I do know that quantum mechanics basically demands that information must be conserved. And if I remember, that's what Susskind believed in, and that Hawking thought that the information is not conserved. My understanding, and I could be wrong on this, is that right now, most physicists would side with Susskind, that somehow the black holes do in fact preserve the information of what falls into them. But it's been, you know, like, it's been a big controversy among that very specialty field of physics for quite a long time. And I don't know enough really to have my own opinion on which side's likely to be right.
Mario, you got your hand up again.
Yeah, this one is actually for Bob. So I did read Suskind's book, and I still don't understand why he insists that the information is preserved. I don't see how it could be. And you know, I'm just befuddled by the whole thing. Do you have any explanation about what he's trying to say? I don't get it.
To be honest, I've never read his book, although I've read parts of it, and I've listened to lectures and interviews with him, and I don't really understand it at a level where I'm kind of like you, Mario, where I'm afraid if I said anything, it would be, I would get it wrong. But I do know that he's I think he's still alive. I think he's very much still alive.
Well, he talks about this holographic principle, and everything is imprinted on the event horizon, and the information never goes away. Isabel, I think, is much more intelligent than you. Maybe she can answer that question. I've known Bob a long time. I can say things like that.
Yeah, I don't know either, to be honest. I think it's just a very difficult to test theory, because you can't really do anything to test it. So,
which
I mean,
makes
maybe
it
one day we'll
philosophy.
be able to. Yeah, exactly. It's more about how, like, what you believe information to even be on a fundamental level and that kind of thing. So
yeah, but if you change, if by quantum mechanics, if you change to just a set of elementary particles, if you go into a singularity, how can information be preserved? I don't get it. I just don't understand that. And I've read his book, and I still don't understand it.
Yeah, I mean, once again, it's like, if singularities, I mean, my understanding is that if you took a poll of physicists who study, the structure of a black hole, you might get a majority who believe that there is no such thing as a singularity, that somehow nature, through physics that we do not yet understand, the physics will prevent a singularity from forming, and that same physics will somehow preserve the information of what fell into the black hole. I mean, it's interesting, both quantum mechanics and relativity are incredibly successful theories, but they don't work together. So we know we don't have the final, even if there is a final theory. So I think a lot of these questions will remain unresolved until we get a final theory. I think the expectation is that if we're going to have to modify one of the two theories, it's more likely that relativity is the one that would have to be modified. So, that Einstein, as great as his theory is, just like relativity modified and improved upon Newton, there's some future theory that's going to modify and improve upon relativity. And maybe that theory will shed light on what happens inside a black hole and whether that information is preserved. And I know there's scientists who are working on it. My problem with string theory is there's like many different versions of string theory. And this is something where, Mario, you've criticized multiverse theory before in
don't go
numerous
off on that again.
conversations. That like there's theories of string theory that predict there's like 10 to the 500 power different possible universes, and you have this landscape of universes where every universe has like a different physical law, and we just happen, when inflation happened in our universe, that kind of selected one of 10 to the 500 power different possible landscapes for our universe, so that different universes have different physical laws. And none of this is testable because you would need a particle accelerator the size of the solar system. So when I hear stuff like that, I get very, very skeptical of string theory. And I remember one night before an amateur telescope makers of Boston meeting, we were having dinner at Changsho restaurant, and I was sitting next to Alan Guth, who was speaker that night. And I was talking to him about that. And he said he totally agreed with me. And then when he gave his talk to the club, just like an hour later, he had a slide in which he outlined that idea. And then he added the words desperate last resort was the word. I remember that very clearly, desperately last resort, that in my view, to revert to that theory, it's a desperate, like everything else has to fail. So my gut feeling is that we will eventually get a better theory to merge quantum mechanics and relativity, but it might have little or nothing to do with string theory. But I've
All
been reading.
respect to Alan Guth, he didn't convince me that night. You've been trying to convince me since. I don't believe in the multiverse. I'm sorry.
Yeah. Well, and the thing is, you can believe in a multiverse and not believe in string theory. But if you believe in string theory, you pretty much have to believe in a multiverse. At least that's how I understand it. But Guth definitely was extremely skeptical of the idea that we have this landscape from string theory with like 10 to the 500 power different universes, with different possible physical laws. I've also had a long talk years ago with Michael Turner, who's a physicist at Fermilab, and he very much agreed with me that, that he just, but again, you get people like Brian Greene, you get your string theorists, and they make very convincing arguments too. But I'm more on the side of skeptics like, Guth, Michael Turner, Lee Smolin, who are very skeptical of string theory.
It sounds like string theory is really good for science fiction writers and movie makers.
Yeah, it
All the
is.
possibilities.
Yeah, that's right. You got 10 to the, and the idea, not, and Mario's going to hate me for bringing up this idea. The
There are
idea
reasons
is
for
that you've got enormous possible universes with different physical laws, and the overwhelming majority of them would have physical laws that do not allow life to exist. So we exist in a universe that have physical laws that allow life to exist because we couldn't exist in another type of universe. And that is like anthropic reasoning. And that explains why we live in a universe that allows physical laws for life. Now, a big promoter of that idea is the Astronomer Royal of Britain, Sir Martin Rees. He wrote a whole book about it that I read years ago called Just Six Numbers. And he's very much a proponent of the idea that there's enormous numbers of universes. We're in a multiverse. Most of them are sterile. We're in a universe with life because we couldn't exist in one otherwise. And that means our very present self-selected our universe to have a very particular set of physical laws to enable life to exist. It's sort of a weird argument. I don't know if I believe in that, but it's a reasonable argument, may or may not be true.
So on that stunning Ouroboros of an idea, I think I'm going to call this evening to a
Yep.
close.
Thanks, everybody.
I want to compliment you again, Bob. That was a terrific presentation.
Let's-
I'll send you a link to the YouTube when we get it up there.
Okay, great. Thanks. Thanks, everybody,
Thanks
for
everybody
tuning
for
in.
coming. Everybody else, all you Gacksters, all you
Thank you,
brand new
Mike.
Gacksters that in a very innocent way made eye contact with me or someone else. Welcome to the club. I'm going to turn off the lights now. Thanks a lot,
Take
everybody.
care, everybody.
Thank you,
Night,
everybody.
everybody.
Thanks, Bob.
Bye.
Thanks, Bob. Thanks, everyone.